It is my pleasure to introduce Andrey. I'm sorry, I'm so unprepared. Andrey Lazarev from Lancaster University, and he's going to talk about global Koszul duality. Please start.
Right, just a small correction, Lancaster University, but it's close enough, some 50 miles from Manchester. Right, yeah, thank you very much for giving me this wonderful opportunity, first time for me. I'm sure there will be some hiccups, but nothing I'm sure that we couldn't handle. I'd like to talk about global causal duality, which is my joint work with my PhD student, Ai Guan. Right, so causal duality. If you thought about causal duality as much as I did, then you realize that it's kind of pervasive. It exists on many levels, and it's kind of ubiquitous in the whole of algebra and geometry. In particular, it exists on the following levels: operatic levels, operatic level, so that would be a duality between an operad and a cooperad, or maybe a duality between one operad and another operad if you just dualize and don't distinguish much between an operad and a cooperad in this way. So for example, the Lie operad is dual to the commutative operad, and vice versa. The associative operad is self-dual. There is a causal duality. There is another level, one level down, as it were, between algebras and coalgebras over causal dual operads. So for instance, that would be duality between Lie algebras and commutative coalgebras, okay, or between associative algebras and associative coalgebras. And then there is the lowest level, the duality between modules and comodules over Koszul dual algebras and coalgebras. Okay, so each level somehow is to do with the level one above. So the third level, the lowest level, duality between modules and comodules, kind of presupposes some kind of causal duality on the associative level. Okay, so that would be the duality between modules over an associative algebra or differential graded associative algebra, and comodules over its Koszul dual. And it is the third simplest level that is most relevant to this talk. Right. Just a few words about what this is, and then later on I will elaborate on that. Given a differential graded algebra, its causal dual, and oftentimes I will abbreviate causal dual or causal duality as simply KD. So given a DG algebra A, its causal dual is a certain coalgebra which I will denote BA. B stands for bar construction of A. It is conilpotent. And I'm not saying what conilpotent means just yet, but later on I will say what that means exactly. Okay, so causal duality that I'm interested, or the one that's relevant here, is an equivalence of certain triangulated categories. So here I have, on the left-hand side, I have the usual derived category D of A, right? So right now I'm here at this line. So on the left-hand side of this duality is the derived category of A, just the usual derived category of a differential graded algebra. And if you don't like differential graded algebras, then you might just consider it usual algebras. They still have their derived categories. Okay, so that's on the left-hand side. And on the right-hand side, I have what I denoted D2 of BA. Okay, so BA is a coalgebra BA, right? And D2 stands for the derived category of second kind of comodules over BA. Again, I'm not going to give you precise definitions just at the moment, but later on I will in a more general framework. My goal will be to construct a non-conilpotent version of causal duality. And I will start with giving you a motivation for this goal, because otherwise it might seem a little bit strange. Okay, there are two pieces of motivation for me. First is to do with infinity local systems. Infinity local systems on topological spaces, or maybe smooth manifolds really. And the other one is derived categories of coherent sheaves on complex analytic manifolds. Right, and I'll spend a couple of minutes talking about infinity local systems, and then maybe a few seconds about derived categories of coherent sheaves. Let me just remind you a very classical, the simplest version of the Riemann-Hilbert correspondence. It's been around for many decades, and perhaps when it was first formulated, it wasn't even called Riemann-Hilbert correspondence. One of the earliest occurrences of this result was a paper of Milner, which was written in middle of 50s or something like that. Okay, so it's possible that it was known even before that. Right. So what is this correspondence? It's a certain equivalence of categories. Okay, so we're here now, and on the left-hand side, this category is the category of locally constant sheaves on a smooth manifold M, right? So perfectly well-known and classical category. On the right-hand side, we have the category of flat vector bundles on M. And what I call the classical Riemann-Hilbert correspondence is a very simple statement which says that the two categories are equivalent to each other. And there is an intermediate category which is used to construct such an equivalence, the category of representations. So we're here, the category of representations of the fundamental group. Okay. Now it's very well known that that locally constant sheaves are the same as representations of the fundamental group, so I won't spend time on explaining that. Now, given a representation of a fundamental group, you can construct the corresponding covering of M and then the associated bundle, and that would be a flat vector bundle on M. Conversely, given a flat vector bundle on M, you look at the corresponding monodromy representation of the fundamental group, and you get a representation of the fundamental group. Okay, so that's how this correspondence works. Okay, now a flat vector bundle is determined by a connection form. Okay, this connection form is a one form on a manifold with values in the endomorphism bundle of your given flat bundle. Okay, this connection form is supposed to satisfy the famous Moore-Cartan equation: dw plus 1/2 d omega plus 1/2 omega omega is equal to 0. Okay, and then if you look at the de Rham complex on M with coefficients in E, then supplied with the twisted de Rham differential, it becomes a complex and in fact a differential graded module over the de Rham algebra on M. So the twisting here is given by adding this twisting term omega. Okay. So the lesson that we're going to learn from this is that a flat vector bundle gives rise to a differential graded module over the de Rham algebra. Right. So if you do it a little bit more carefully, then we see that there is actually a functor which associates to a local system or a representational fundamental group or locally constant sheaf, a differential graded module over the de Rham algebra on a manifold. Okay. So here's a natural question, a natural and extremely naive question then that one could ask in this context. Is this functor an equivalence of categories in some sense? Now, certainly it couldn't be an equivalence of categories on the nose. So maybe a better question would be to take derived categories on both sides and ask whether this is an equivalence of triangulated categories. Certainly, there is a well-defined and nice derived category of pi1 of M, right? Representations of the fundamental group of M. And similarly, we could consider the derived category of any differential graded algebra, such as omega star of M, and that again will be a triangulated category. So are these triangulated categories equivalent? Could this functor be extended to an equivalence of this category? Well, turns out that this is not true, okay? Derived categories of the fundamental group and the derived category of the de Rham algebra are very much inequivalent. One reason is that the left-hand side being the derived category of the fundamental group, only depends on pi1, okay? Whereas the right-hand side may be non-trivial even when the fundamental group is trivial, right? In the simply connected case. The de Rham algebra might have quite a non-trivial derived category, even in a simply connected situation. Okay, here's another attempt, and we're here now. Let's replace the left-hand side by cohomologically locally constant sheaves on M. And what do I mean by that? A cohomologically locally constant sheaf is not really a sheaf, but a complex of sheaves. It's a complex of sheaves such that its cohomology are locally constant sheaves on M. All right, so this category, or maybe it's derived category, it's better to say that we're considering the derived category, certainly depends not just on the fundamental group of M, okay? So that's a bit of an improvement. So is this an equivalence? Turns out that this is still not an equivalence. And the reason is this time that the right-hand side is insufficient to recover the information which is to do with the fundamental group this time, okay? So the derived category of the de Rham algebra forgets too much about the fundamental group. For example, if we consider the real projective space, RPN, then its cohomology with real coefficients, say, is 0, right? What that means is that the de Rham algebra is quasi-isomorphic to K, to R, okay? And therefore, its derived category is pretty much trivial. It's the same as the derived category of R. On the other hand, there's clearly non-trivial representations of pi1 of RPN, which correspond to some non-trivial flat vector bundles on RPN. Okay. So here's, nevertheless, that step that we have taken, namely replacing the derived category of pi1 of M with the derived category of pi1 of R, the derived category of cohomologically locally constant sheaves was a correct one. So here's the correct generalization, which is due to the work of Bloch and Smith, and also Chuang, Holstein, and myself. So this formulation was due to Chuang, Holstein, and myself. Bloch and Smith gave a different formulation using the language of A-infinity functors and A-infinity local systems. Right, so we're here now at the correct generalization. On the left-hand side, we still have the derived category of complexes of cohomological locally constant sheaves. Okay. On the right-hand side, we have the homotopy category of twisted modules over the de Rham algebra. So on the face of it, it looks like it might be quite close to the derived category, but I need to tell you what a twisted module is. Okay. So what is a twisted module? Actually, let's forget about twisted modules for just a moment and recall how the derived category of a DGA is defined. Okay, we just consider cofibrant modules over a given DGA, and then we'll look at homotopy classes of maps. Right. So that's how the derived category is formed. So the difference between this construction of a derived category and what's in the right-hand side of this equivalence is that I'm replacing cofibrant omega star of M modules with something that I call twisted omega star of M modules. Okay. Now, what is a twisted omega star of M module? It looks a little bit like a cofibrant omega star of M module. Okay. Although it's not really. Okay, it's more general. It's something more general. There are more twisted modules than there are cofibrant modules. All right, so here's a so-called elementary twisted module. We take omega star of M and we tensor it with a vector space. Okay. Finite dimensional vector space. And then we supply it with any differential whatsoever that is compatible with the omega star of M action. In other words, what we get in the end is a differential graded module over omega star of M. There's no restrictions on the differential. That's important. So in some sense, it is easier. It's maybe not more natural than the notion of a cofibrant module. A cofibrant module is something similar, except that there's some restrictions on D. It has, or maybe on the whole thing. There's supposed to be some kind of filtration, and and D is supposed to be triangular if you write it down as a matrix, things like that. Anyway, even if you don't know what a cofibrant module is over a DGA, you now know what a twisted module is. Okay, so this what I wrote here is kind of an elementary twisted module, and then you do the usual thing. You take filtered direct limits and you take retracts, and you can call this a more general twisted module. Okay. So in this sense, I would like to reiterate: if you consider not an arbitrary D, but something that respects the filtration, and then you do this filtered limits and so forth, then what you get is precisely the notion of a cofibrant module. So a twisted module is something more than a cofibrant module, more general, I should say. A cofibrant module will be twisted, but not vice versa. For example, V could itself be one-dimensional. All right, that's quite possible. If it's one-dimensional, then there is no way that omega star of M could be non-trivially a cofibrant module over itself. Okay, the only way that it's a cofibrant module over itself if it has its own differential. But if you consider it as a twisted module, it could be twisted in a non-trivial way. Okay, so I've spent quite some time ranting and raving about twisted modules. So twisted modules are play the role of cofibrant modules in the sense that the derived category of second kind is formed by taking twisted modules and looking at its homotopy category. Okay, just morphisms are chain homotopy classes of maps. Okay, and with this definition, it turns out that this equivalence holds. Okay, so the derived category of cohomological or locally constant sheaves is equivalent to something that could be called the derived category, an exotic derived category of omega star of M. There's a similar story if M is a compact complex manifold. Here, we're now at this line. Here, the left-hand side is the derived category of coherent, okay, so that's coherent analytic sheaves on a compact complex analytic manifold M, okay? So that's somewhat analogous to this, okay? And the right-hand side, well, again, it's similar to what we have previously, but the role of the de Rham algebra is played by the Dolbeault algebra. Okay. So I think this is kind of interesting that a category which captures the global phenomena, such as the category of coherent sheaves on the left-hand side, could be equivalent to something that looks kind of affine. Okay. So derived category of modules over a single differential graded algebra. So this formulation also belongs to Chuang, Holstein, and myself, although a very similar and pretty much equivalent formulation was given by Bloch quite a long time ago, and maybe 10 or 15 years ago. Okay, so these two pieces of motivation lead one to the following natural question, I think, question. Whether there exists a model category structure of differential graded modules over a differential graded algebra so that twisted modules are cofibrant, okay? I just told you that they weren't cofibrant, but of course, what I meant was that they weren't cofibrant with respect to the standard closed model category structure on DG modules. And the answer is that yes, there exists a certain model category on DG modules, and moreover, as an added bonus, this is part of a certain Koszul duality pattern. And this is something that I'm going to spend a little bit of time explaining, just the usual ordinary, that is conilpotent Koszul duality, and then how it could be generalized. Maybe I should pause here and ask whether there are any questions. No? Fine. Right. So, and before I go to causal duality, let me just make a bit of a digression and talk about coalgebras and pseudo-compact vector spaces. So we're now here. This is very classical and very old, although the way that this material is presented might be considered as slightly unusual. So first of all, let me introduce the notion of a pseudo-compact. PC stands for pseudo-compact differential graded vector space. So what is this? Is that we take the category of finite dimensional differential graded vector spaces, and then we take its pro-category. In other words, projective limits of finite dimensional vector spaces. Any category has a pro-category, okay? So a pseudo-compact vector space is then a projective limit, like so, and morphisms between two such projective limits are given by this formula. Notice that the category of pseudo-compact vector spaces, so we're talking, we're at this line now, the category of pseudo-compact differential graded vector spaces is anti-equivalent to the category of all vector spaces. This is because the category of vector spaces is the int category of finite dimensional vector spaces. Every vector space is a union of its finite dimensional vector spaces, okay? So it's if it's the int category of finite dimensional vector spaces, then the pro category will be anti-equivalent to it. Okay. Moreover, the category of pseudo-compact vector spaces is symmetric monoidal under the following tensor product. Okay, so we have one pseudo-compact vector space and another, and we just tensor them component-wise and then take the limit. Well, once we have a symmetric monoidal category, we can talk about monoids in this category. Okay, monoids in this category will be called pseudo-compact differential graded algebras. And then once we have monoids, we can talk about their modules. Okay, so we can talk about pseudo-compact modules over pseudo-compact algebras. There's an interesting and non-trivial fact.
Can I ask a quick question?
Yep.
Did you define pseudo-compact differential graded vector spaces just as the opposite of differential graded vector spaces, or can you repeat the definition, the original definition?
You can define it like that. Yeah.
Okay.
I mean, I defined it slightly differently, but really almost tautologically the same. Yeah. If you like to take this as a definition, you should be able to. Yeah. Just the opposite to the category of differential graded vector spaces. Right. There's a non-trivial fact. Okay. Non-trivial because it uses associativity in a very essential way. Any pseudo-compact differential graded algebra is a projective limit, inverse limit, of finite dimensional differential graded algebras, and similarly with modules. You might think that it's kind of the definition already, but no. I think you can see that the difference is there. It's subtle, but it's there. Okay, we know that a pseudo-compact DGA, since it's an object in pseudo-compact vector space, it must be a projective limit of finite dimensional vector spaces, right? But why is it a projective limit of finite dimensional DGAs? So that's a bit more subtle. And for example, that wouldn't be true for a pseudo-compact differential graded Lie algebras. Okay, an interesting fact. Right. So pseudo-compact differential graded algebras are intimately related with differential graded coalgebras. In fact, they're anti-equivalent to it. Okay, given, so we're now here. Okay, so given a coalgebra, and I didn't give a definition of a coalgebra, but I hope that I shouldn't give it, right? It's a comonoid in the symmetric monoidal category of the differential graded vector spaces. So given a differential graded coalgebra, I take its linear dual, get a pseudo compact algebra, okay? That's because the linear dual to any vector space is a pseudo compact vector space, okay? So this here could be viewed also as a theorem, okay, rather than as a definition. Given a differential graded vector space, I take its dual, okay? It was previously an inductive limit of its finite dimensional vector space. When I take a dual, it becomes a projective limit, okay? So it's a bit of a theorem, if you like, although a very simple theorem. Conversely, given a pseudo-compact vector space, you take its continuous dual and you recover your original vector space, okay? So similarly, if you have a coalgebra, you dualize, you get an algebra. If you get a pseudo-compact algebra, you continuously dualize, get a coalgebra. So we have this equality of categories. And a differential graded coalgebra is called conilpotent if its differential graded pseudo-compact algebra is local. In other words, it has a unique differential graded two-sided maximal ideal.
Andrey?
Yeah.
Where are augmentations and co-augmentations in this discussion?
So far, there are no augmentations and co-augmentations.
Okay.
Okay.
So let me ask one more question.
Yeah.
Oh.
There are a couple of examples.
Yeah, I was going to ask, how do you understand this condition of conilpotency as something in the usual iterated applications of the coproduct vanish?
It's equivalent.
It's equivalent.
It's
Okay.
equivalent. Yeah. It's not difficult to prove that it's equivalent.
Okay, but you're not requiring a co-augmentation, because I've also seen this definition in which you take the co-augmentation co-ideal.
Yeah.
And then you ask for the coproduct to vanish after iterated applications there.
Yeah.
But you are not requiring any co-augmentation in these definitions.
No,
Okay.
don't think so. No.
Okay.
You have a co-unit. You would need a co-unit, right? And that condition that you're talking about is a condition on the kernel of the co-unit.
On the kernel of the co-unit. Yeah. Okay.
Yeah. Okay. Here's a few examples, just to help you orient with those notions. So if V is a vector space, okay, we're here now. We can consider its tensor coalgebra, which looks like a tensor algebra, except that it's a coalgebra with the following co-multiplication, right? Then it's conilpotent, because if you dualize this coproduct, then what you get is the completed tensor product on the dual vector space. Well, completed in the sense that you take form of power series rather than polynomials, non-commutative polynomials. Well, here's a very simple-minded and uninteresting example of a non-local pseudo-compact algebra. Okay, this algebra is even finite dimensional, so it's just a product of k and k. It's not local visibly, right? If you dualize it, then the corresponding coalgebra will not be conilpotent. Okay. Later on, we will consider more interesting examples of non-conilpotent and non-local situations.
Andrey, one more question. I'm sorry.
Yeah.
When you define this coproduct and the tensor coalgebra, you're starting with k equals to 0, right? So the first term of this sum,
yeah, one tensor, yeah. Mm-hmm. Yeah. Right. Okay. I'm now here at the notion of a pseudo-compactification. Given a DGA, so A is a DGA, we can pseudo-compactify it, and the result will be denoted A check. So what this is the completion of A at all two-sided differential graded ideals of finite codimension. That's a huge thing. And here's an example of how it works. Consider an algebraically closed field, and algebraic closure is assumed just for simplicity. For a non-algebraically closed field, we can also say what that is, but it will be slightly more complicated. Okay, so if K is an algebraically closed field, and we look at the polynomial algebra in one variable, then its pseudo-compactification is this enormous thing, okay? It's a product of formal power series in one variable indexed by all elements in K, okay? So let me just tell you how you can get that. That's actually very easy, okay? You have K of X, and you look at the ideals of finite codimension. Well, K is algebraically closed. You might as well consider maximal ideals. So what are the maximal ideals? Maximal ideals are precisely points of K. Okay, if you just complete at 0, okay, the maximal ideal, X, right? Then you get one copy of formal power series of X. But then you complete everywhere else. And this is where you get this enormous product. Okay, here's another example of a slightly more topological nature. If X is a simplicial set, then you could look at its cochain algebra. Okay, so we're now here. C star simplicial of X. It's a pseudo-compact DGA because its dual is a certain coalgebra of chains. Okay, it is local, this pseudo-compact DGA, if and only if X is reduced. In other words, it has only one vertex. So this vertex corresponds to the unique maximal ideal. If there are several vertices, if there are 2 vertices, for example, then there will be 2 maximal ideals and so forth. Okay. Okay, now let's go back to causal duality. Okay. And I would like to formulate the standard, well, more or less standard version of causal duality using the notions that I've just introduced. So let's say that A is an augmented DGA. Now, the fact that it's augmented, this condition that it's augmented, is not necessary, but it leads to some simplifications, okay? It's possible to formulate everything in the non-augmented case. Nevertheless, all the ideas are already present in the augmented case. So we have an augmentation epsilon from A to K, and I denote by A bar the kernel of this augmentation. Now the bar construction of A, which I will view now as an algebra rather than a coalgebra, using this correspondence between pseudo-compact algebras and coalgebras, will be the following thing. Okay, so I take A bar, I take its dual, I take its desuspension, I take the tensor algebra over it, and I complete it. Okay, complete in a usual way, so that instead of having non-commutative polynomials, I have a non-commutative power series. And then there is a certain differential D, which is induced by the internal differential on A and the product map, A tensor A into A. Okay, so I hope that that you've seen this construction already. Okay, differential D squared is equal to 0 as follows from the associativity of the product on A and the squaring to 0 of the internal differential on A. Okay, so that's the bar construction. What's the Khobar construction? The Khobar construction is a functor that produces a DGA out of a pseudo-compact DGA. Or, if you prefer, you can dualize and start with a coalgebra and and construct this functor. Okay, so the construction is pretty much the same. So A here, we're here, right? A is a local pseudo-compact DGA. Instead of taking the kernel of the kernel of the augmentation, I take the maximal ideal, okay, denoted by A bar. Take the dual, take the desuspension, take the uncompleted tensor product, okay. Notice that when A is pseudo-compact, or A bar is pseudo-compact, then the dual is not pseudo-compact. So we're in good shape taking the non-completed tensor product, right? And then there's D, which is again induced by the internal differential and the product. So that gives an adjunction. And we're here at this adjunction. This is a contravariant adjunction. Or if you put op on the right-hand side, then it will be a covariant adjunction between differential graded augmented algebras and pseudo-compact and the opposite category of pseudo-compact differential graded local algebras. Or if you dualize, then on the right-hand side, we would have pseudo-compact coalgebras. Okay.
You would have nilpotent coalgebras, right? Or conilpotent.
Conilpotent coalgebras, yes. So, so this category, okay, is equivalent to category of differential graded conilpotent coalgebras, by definition, if you like. Right. So this bar-cobar adjunction can be.
Sorry to interrupt. Is the conilpotency condition used in showing that it's an adjunction or showing that it's an equivalence?
I think it's both, actually. Both.
Okay.
Yeah. Right. So this bar-cobar adjunction can be improved to a certain Quillen equivalence, as proved by Hinich, Keller, Lefebvre, and Posadzelsky. But I don't want to dwell on that. Okay. I have about 5 minutes, right? Or something. Or 7 minutes. Is that right? Okay.
Yes, that's right.
Okay, so slightly behind, but not much. Right, so I'd like to talk about the module level causal duality, as it's more relevant to what I'm going to say. Right, so again, let A be an augmented DGA. Then there is a certain adjunction between the category of A modules or differential graded modules and pseudo-compact modules over BA. When I say pseudo-compact modules over BA, those are the only modules that we have over BA, right? Because BA is a pseudo-compact algebra. And just as before, it's a contravariant adjunction, and if you want to make it covariant, then you have to put an op, say, on the right-hand side or the left-hand side. I'm putting op on the right-hand side, so in this way, it resembles, or becomes, I should say, the familiar adjunction between A modules and BA comodules, where BA is viewed as a coalgebra. Okay, so I don't have much time to describe that in detail, but one functor here is actually can be described very easily using classical notions, okay? So given M, an A module, we dualize it, okay, and view it as an A bimodule, okay? It's certainly a right A module because you dualize, right? But also it's a left A module using the augmentation of A, okay? So I'm using, I'm considering M star as an A bimodule, and then I take the Hochschild cohomology, the reduced Hochschild complex of A with coefficients in M star. So that's one of the functors. okay, from left to right. The other functor, it's actually simpler, but maybe not as traditional as this one. And we have a theorem, so we're here, which says that if R is a pseudo-compact DGA, then there is a model structure on the right-hand side here, okay? In fact, there is a model structure on all, pseudo-compact R modules, irrespective whether it's a bar construction or not, okay? And under this model structure, this adjunction becomes equivalence with the usual model structure on, with this model structure on the right-hand side and the standard model structure on the left-hand side. So the category of modules over a DGA has a model structure, okay? The homotopy category is the usual derived category, okay? And with respect to this model structure, this is a equivalence. So in particular, we would have an equivalence of the derived categories. And what we have in the right-hand side is sometimes called the derived category of second kind. Okay, I have 2 more slides. Right. So let me just say a couple of words about the model structure on pseudo-compact modules and why this is called the model structure or the derived category of second kind. So we're now here, and R is a pseudo-compact DGA. Then again, a twisted module, something that we've seen already, over R is an R module of this form, okay? So you can see that this is exactly as the same as before, except that here R is a pseudo-compact algebra. And we say that 2 modules, 2 pseudo-compact modules, M and N, are weakly equivalent, and we're here now, if and only if the following holds. So what does it mean? I'm using my twisted modules as some kind of spheres, okay, which detect weak equivalences. Think of twisted modules as spheres. I previously, or rather, previously we would have a sphere being just R, our algebra A, okay, or R. So in particular, if we take R, if we take L to be equal to R in here, what we have is that M and N are simply quasi-isomorphic. This condition just says that M and N are quasi-isomorphic with this particular choice of L. And it turns out that in order to construct the usual derived category, this is all that's needed, but not here. Here we need to take arbitrary twisted modules instead of just R. Okay, and then fibrations are just surjections. Turns out that the category of pseudo-compact R modules, or rather the opposite to it, is a cofibrantly generated model category, and its homotopy category is a compactly generated triangulated category. Okay, so again, recalling that pseudo-compact algebras are the same as coalgebras, we could recast it in terms of comodules. So the category of comodules over R star, which is just the linear dual to R, has a model category such that its homotopy category is triangulated and compactly generated. Okay, this category is equivalent to the if R is BA, the bar construction of some A, then this category of comodules is equivalent, the derived category of comodules is equivalent to the usual derived category of A. And I'm almost out of time, but I only have 1 slide. So probably I will be over time by a few minutes, by a couple of minutes. So the non-conilpotent generalization. Okay, so A is now an augmented DGA. And what I'm going to do is I'm going to replace the usual Khobar construction. Sorry, that should be bar construction, not Khobar construction. I'm going to replace the bar construction of A with what I call an extended bar construction of A, which is constructed as follows. Now, I'm sweeping certain things under the rug here, but not very important things, okay? So what I do is I take A, I take its dual, I take the desuspension, then I take the tensor algebra, okay? It turns out that without completion, there is a differential there. That's a slight lie, okay? But if you could just let it slide, then nothing will be lost, okay? Suppose that it's that the differential is well defined. It's actually is well defined if A is finite dimensional. If A is not finite dimensional, then you have to work a little bit harder, okay? But then what you do is you just pseudo compactify it rather than complete it at the maximal ideal, at the natural maximal ideal. You complete it everywhere, okay? And you called it the extended bar construction of A. And then, just as before, you can construct a certain adjunction between A modules. So we're now here. We're in a DG category of A modules and pseudo-compact modules over this extended bar construction. And then the theorem, which I wanted to tell you, and now I'm telling it, is the following. There is a model category structure on the left-hand side this time, okay? Remember that we already have a model structure on the right-hand side. It's already exotic. On the left-hand side, it will also be exotic, even though A is just an ordinary algebra, okay? So in some sense, it's more exotic than other exotic categories, okay? So there's a model category structure on the left-hand side so that this adjunction is equivalence. Okay, so I'll just tell you what this model structure is. First of all, the most important thing is, of course, the notion of a weak equivalence. And I already said what it is. It's exactly the same as for pseudo-compact modules, except they don't need to be pseudo-compact. We have twisted modules. We use them as spheres, and we use them to detect weak equivalences, okay? So M and N are weakly equivalent if they're quasi-isomorphic as seen from the eyes of any twisted module L. And then vibrations are surjections. The last thing that I'd like to say is to give you an example to illustrate how different this category might be from the usual derived category of an algebra. So here, A is lambda of X, the exterior algebra on one generator in degree 1, okay? What happens if we just take the usual bar construction of this? Well, the augmentation ideal here is just one-dimensional. And then we suspend it or desuspend it, it becomes in degree 0, and then we take the polynomial algebra, but we don't stop here. We pseudo-compactify it, okay? So we get this enormous thing, okay? So the upshot is that the pseudo-compact modules, or the homotopy category of pseudo-compact modules over this enormous thing is equivalent to the category, to this exotic category of second kind of this modest finite dimensional, two-dimensional algebra with this exotic model category structure. And the compact generators of this category are quite interesting. And they're given by complexes of length 2 such that d of 1 equals alpha x. Notice that all of them are acyclic. So in the usual derived category, they will be trivial. And I think this is it. This is all I wanted to say. I'm 5 minutes over, and I'm sorry about that.
Well, thank you, Andrey. I don't know if we want to try to clap. I wonder how that sounds. I'm going to unmute everybody. Let's thank Andrey.
Yeah, I can hear that loud and clear.
I heard a few things. Anyway, mute everybody again. Oops, unmute Andrey. Let's ask you some questions, Andrey. Can I start with a question? Is this theorem gives the module structure from slide number 5, where you asked the question? Is that did I understand that right?
Sorry, I didn't quite get it. Is this model structure what?
Is this the model structure you were asking for in slide number 5?
Exactly. You mean infinity local systems and so forth? Yeah, that's the one. Yeah.
So the twisted modules are now the cofibrant objects in this model structure.
Yes. Yeah. So if you look at the Ram algebra or the Dolbeault algebra, then indeed there is a cofibrantly generated model structure of modules over it, which has this natural geometric meaning. Edgar, okay, that's my son. Edgar, yeah. Sorry about that. As you can see,
are you ready for more questions?
Yeah, I'm ready for more questions.
Well, Manuel.
So, what do you have any interpretation to what you get if when you consider the category let me say when A equals chains on the base loop space of a space, and you consider A modules with this model structure?
Right. Yeah, you see, somehow this question. Okay, so what am I going to say? You see, when you take, yeah, that's actually a very good question. Even though I wanted to say that it didn't make sense, but actually did make sense in the sense that it could clarify what can be done and what cannot be done in this context. If you have a differential graded algebra A, then normally its derived category is an invariant of its quasi-isomorphism class. So if you have another algebra B that is quasi-isomorphic to it, differential graded, yeah, then it has the same derived category. Okay, that's not true here. So this is the next part of the project, which I didn't tell you anything about. Okay, and which is to do with causal duality one level above. So does there exist a certain weak equivalence on algebras, okay, which had better be stronger than quasi-isomorphism, so that two equivalent algebras have equivalent derived categories of second kind? And the answer is kind of yes, but it's a little bit technical, and I don't want to get into it right now, okay? Certainly this this relation is stronger than a quasi-isomorphism, closer to an isomorphism, okay? Now, back to your question. When you have a space and you take its base loop space and then you have chains, then as far as I know, it's only defined up to quasi-isomorphism.
Good. Yeah.
And
but you can consider the stronger weak equivalence class of the singular chains on the base loop space under this stronger notion of equivalence.
Yeah, but it will all depend, for example, on what sort of chains you're taking,
Right.
What sort of model for the space you're taking.
Right.
You know, you have one simplicial set and you have another which is weakly equivalent to it. Will it give rise to equivalent chains? I don't know.
So let me ask one more question along this
Manuel,
line.
let's let some other people ask some questions if there are any. And if you still have questions, maybe I will leave the Zoom meeting open and you can discuss that with Andrey further. Is there anybody else having a question? If that is not the case, I would like to stop the recording here. I want to thank you again, Andrey. I think the clapping wasn't a big success, but we are all very thankful that you tried this with us. And I hope that the video turns out well. And thank you so much for your talk. I really enjoyed it.
Yeah, thank you.
Thank you. That was very good.
Thanks.